All right, so this is the colorful diagram that we left off with last time, right? We've got the unit circle here. We've got the angles in pink are the degree measures. The angles in red are the radian measures. And I told you that we had one more item that we were going to take a look at on this circle in terms of filling in. And that's the ordered pairs of the points on the sides. So I'm going to start, and we'll do this in yet another color because that seems like a good idea. Let's see if the purple shows up today. The first ordered pair we're going to start with is right over here. Okay, so on the unit circle has a radius of 1. That's kind of the whole point, is in the word unit circle. Okay, so this is actually on the x-axis. So if we go out to the right, 1 unit, that's an x value of 1. And what's the y value here? 0. Okay, we'll fill in the other quadrantal ones first because they're the easiest ones. Let's go up to the top, that pi over 2 angle or 90 degrees. What is that ordered pair right here?
0.
Right. So this is 0, and then we've got a y value of 1. Over here on the right-hand side, this angle of pi, what is this ordered pair?
Negative 1, 0.
-1, 0, because we're on the left-hand side of the graph. And then we've got the ordered pair at the bottom. And what's that ordered pair?
0
0 and
and negative 1.
-1. Okay, so those just follow the same. You could have done that in algebra. That's nothing exciting. The other 3 in each quadrant are going to be mirror images of one another. And here's what I mean. This first one we've already established right here. This actually corresponds to a 30, 60, 90 triangle. We've got a 30-degree angle there in pink, right? And if I dropped a line segment, and I'll do it just to show you, but then I'm going to erase it. If I dropped a line segment down here, I would create a triangle. Agreed? Okay. That triangle would have a 90-degree angle down here at the bottom, right here. Yeah? And up there at the top where I started my line, it would actually have a 60-degree angle. So this is a 30, 60, 90 triangle. Yeah? Okay, and we've already looked at 30, 60, 90 triangles back in section either 2.3 or 2.4. And we talked about those side lengths, and remember I ratioed them out so that they had a radius of 1? I didn't call them radius, we called them hypotenuse. Yeah? We said, okay, well if we make the hypotenuse of length 1, then we end up getting some of these different kinds of values. And that's the hypotenuse. In fact, let me put it back in. That hypotenuse right there is in fact the radius of this circle, and the radius of this circle is 1 because it's a unit circle, all right? So this ordered pair right here is one you've seen before. This ordered pair is the value square root 3 over 2 and 1/2. And sometimes in terms of memorizing these, and this is how I remember, square root 3 is a bigger number than 1. It just is. If you put square root 3 in your calculator, it's going to spit you out something a little bit bigger than 1. So the square root 3 over 2 is a bigger value than 1. And if you take a look at this value, or this triangle, whoops, let me try that again. If you take a look at this triangle and you compare the y value, or the y height in green that I just made, to the x height, which is along the x-axis of this side of the triangle, the x is clearly longer than the y. Yes? So it makes sense that the x value would be the square root of 3 over 2 and the y value would be the 1/2. Now I'm going to skip the next one because I want to show you what happens up here. If you take this 60-degree angle in pink, well, that's just another 30, 60, 90 triangle, right? Sure. So I actually still get the 1/2 and the square root of 3, but what do I get? Well, I get them reversed. Because all I've done is I've taken that triangle that had those same sides and I've flipped it. Instead of it being sort of long on the bottom, it's long on this side, right, the vertical side. So the x and the y values switch. The 45-degree angle, and again, we've done this one as well, was the square root 2 over 2, square root 2 over 2, which is actually the problem. I think it was Shannon. Am I right? Shannon, were you the one that asked this problem here on the board? Who was it that asked this one? Chelsea, right? Okay, Chelsea asked this one, so this square root 2 over 2 is right here. That's a 45-degree angle, isn't it? So this little piece down here in the thetas, this was a 45-degree angle of some sort that we were working with. So that's where we're seeing that square root 2 over 2's come into play. If you know those 3, you know the rest of the circle. Because every other quadrant has those same points, but they got some negatives on them because we're in different quadrants. And in fact, you don't even need to know all three of those, I don't think. You need to know two of them. You need to know the first one and the second one because the third one's just flipped of the first one. So there's wonderful symmetry here. So we're going to fill them in as we go around. So at 120 degrees, what will my ordered pair be? Close. -1/2. And then the square root 3 over 2. Because it's the same x distance in each direction, right? And the same y height as at 60 degrees. How about the 3 pi over 4? What's that one? Negative square root 2 over 2? Perfect. What about at 5 pi over 6? Perfect. We're halfway done. How about down here at 7 pi over 6? So it's the same ordered pair, but they're both negative, right? And the same thing at 225 or the 5 pi over 4. They're both negative square root 2 over 2. How about this last one down here on this quadrant 3 at 240? They're both negative, so negative what? 1/2. And then negative square root 3 over 2. That's a 2 down there. I can't draw very well that low. And then I've got the 5 pi over 3, 7 pi over 4, and 11 pi over 6. They're the same thing, right? If you take this picture and you flip the mirror image over, it'll be the same ordered pair. So it's going to be the 1/2 and the square root 3 over 2. Which one's negative, the x or the y? The y. So my x value 1/2 is positive. My y value negative square root 3 over 2. My x value square root 2 over 2 is positive. My y value negative square root 2 over 2. And then again, my x value over here is positive, square root 3 over 2. And my y value is negative 1/2. This is the unit circle with all those details filled in. The angles in radians, the angles in degrees, and then the ordered pairs. And so when you come to class on Wednesday, this is what you're going to do for me. You're going to do a unit circle quiz. You're going to get a piece of paper very much like the one that you're working on, right? It won't have the sine, cosine, tangent stuff at the top. It's just going to have the circle. And it's going to have all this, angles marked in there, and you're just going to fill them all in. You have to fill them in with radians, degrees, and ordered pairs. Make sense? Okay. And you're going to need those because we're going to be using them for the rest of the semester. So let's take a look at the sine and cosine values as determined by the unit circle now that we've sort of described them in that way. The first thing we're going to talk about is the symbol for each of them, and you know the symbol for each of them, but then we're going to look at the domain and the range. So the symbol for sine looks like sin, right? Sin x. So this is f of x or y equals sin x. That's what it looks like. And what's the notation for cosine? Cos x. Tangent. Tan x. Cotangent. I'm sorry, cosecant. Give me the next one. Cosecant. CSC. It can't be COS because we've already got that one. So you have it isn't always just the first three letters, I guess is my point. However, for the rest of them it is. What's secant? SEC. And then cotangent. COT. So you're sort of familiar with these. We've been working with these already. What we haven't done, however, is we haven't talked about domain and range. So let's take a look at domain. Domain and range are a college algebra concept. Algebra you've taken a look at before. It has to do with functions. Domain has to do with the input of a function, the x values. What x values can I have? Okay? So if you take a look at the unit circle, let me flip back over here. We've got all kinds of mess on this picture, all right? But the sine values for any angle is always the y value on the unit circle. So this is really nice because if you memorize this unit circle and I ask you what is the sine value of 60 degrees, and you know all of the information on that 60 degrees, so you know 60 degrees is pi over 3 is 1/2 square root 3 over 2, and I say what's the sine value, you should be able to say, oh, the sine value is square root 3 over 2 because it's just the y value there. Okay? Now, if you think about it though, what the question here is asking is sine values, if they're the y values, where do we have y values in this unit circle? What angle measures give me a y value? All of them, right? Yeah, all of them do. I always have a y value associated with the angle measure I'm at, correct? So no matter what angle measure I'm at, I've got a y value there. So when I'm looking at the domain on this, the domain is all real numbers. And I want to show you a notation for that you may or may not be familiar with. It looks like an R with a double line on the left-hand side. That is notation for all real numbers. Now, likewise for cosine, cosine values from my unit circle are all the x values. So what angle measures give me x values? All of them. So my my domain is again all real numbers for cosine. But here's where things are different. Tangent, cosecant, secant, and cotangent are not just the x or the y value on the unit circle. On the front of this last sheet of paper that you filled in that we did last time, what is tangent? It's y over x, okay? Which means there's going to potentially be some problem spots. If I divide numbers, what would be a problem for x to be equal to? 0. If x is 0, then y over x is what we call undefined, right? Where on this unit circle is the x values, or are the x values 0? At the 90 and 270, or some of you are saying on the y-axis, right? If I'm on the y-axis, either at the top or the bottom, at the 90 or 270, or the pi over 2 and 3 pi over 2, I can't have a tangent value. And I can't have a tangent value because the x value is 0, and if the x value is 0, I get a y value divided by 0, and that's undefined. So I can't get tangent values at those angle measures. And I know that you guys didn't use angle measures in terms of radians, but you're going to be using them more, and you're going to be using them right now. So this is going to look really funny because I don't have enough space to write it, but I think you do if you write small. Okay, so in here, this is all real numbers except when theta, or you know what, let me use x because x is written here. When x equals n pi over 2 and n is odd. I shouldn't have used x here, but I did, so we're just going to go with it. This is the x I'm talking about. It's the angle measure. Okay? So this is saying when my angle measure is an odd value, like 135, negative 135, negative 7, negative 243, whatever, times pi over 2, I'm going to end up either at the top of my unit circle or the bottom of my unit circle, and I can't have tangent values there. Make sense? Okay. Cosecant. How do I determine cosecant values from my unit circle? It's 1 over sine, and sine is y. Sine is y. I had a student tell me once that they remembered which one was sine and which one was cosine because it's alphabetical. So cosine becomes before sine cs, right? And x comes before y, xy. So she remembered it by it's alphabetical. All right, so cosecant is related back to sine, and sine is the y value. It's 1 over y. So if I'm looking at my unit circle, where do I have y values that are 0?
0 and 180.
0 and 180, or 0 and pi, right? Whole pi values. And actually, 0 is a whole pi value too. It's 0 pi. So we can express this very similarly, and we can say that we have all real numbers except x equals n pi. And we have to say n is a whole number, or an integer actually is more specific. So I'm going to wish I had more space. I already do. N is an integer. You know what? I'm going to show you something because it'll help me on space. I already showed you it once. We'll do that. Then I've got the space for it. This symbol means is an element of. It means it is, kind of like having an equal sign a little bit. This z is an integer, is integers. Just like the r is for real numbers, the z is for integers. So this is saying n is an integer. You don't have to write it that way, but I need the space, so I'm going to. All right, secant. Secant is reciprocal of cosine, and cosine is which value on the unit circle? The x value, which means that we're going to be looking for 1 over x, which means every place that x is equal to 0 is a problem. But we already found where x is equal to 0, and we already wrote it down once, didn't we? Yeah, so we can just write down the exact same thing that we wrote down for tangent, agreed? So this is all real numbers, except when n equals, I'm sorry, not n equals, x equals n pi over 2, and n is odd. How about cotangent? What is cotangent? Cosine over sine, and cosine is x and sine is y. So this is x over y, which means the problem spots are specifically when y is equal to 0, and we already did that once, right? On cosecant, which is the one that's in the middle here, which means we can repeat that same domain. So this is all real numbers except when x is equal to n pi and n is an integer. All right, let's talk about the range of these things. So we're going to go back over here and think about my unit circle again. For sine, sine is which value? The y value. Sine is the y value. So if you look all the way around this circle, I want you to try and describe for me what kind of y values you're seeing. What's the smallest y value you see anywhere? -1/2? There's a smaller y value than that. Square root 2 over 2 is bigger negative number. Yes, it's a smaller number, but there's something smaller than that. 0 is bigger than any of these negative numbers, but negative square root 3 over 2 is smaller than negative square root 2 over 2. -1, right down here. This right here, in terms of this picture anyway, should make sense. Looking at this picture in terms of the xy coordinate plane, not looking at any of the numbers themselves, where is the smallest y value on this entire picture? It's right here. It's the lowest spot on the graph, right? -1. What's the biggest y value on the picture? +1 at the top, right? So this whole picture goes from -1 to +1 on the y-axis, which means all the y values are occurring between -1 and +1. With me? That means my range over here, sorry, just a sec, is from -1 to +1. This is interval notation. Again, college algebra idea. The brackets mean that I'm allowed to equal the value. I put the first spot and the last spot, and it means everything in between are values that I'm allowed to have. Okay? But that's the range for sine. The range for cosine, well, cosine's my x values. What x values do you see on this unit circle? Yeah, I'm just looking at this axis now, right? The smallest x values over here at -1 and the largest x values over here at +1. So my cosine values go from -1 to +1. Those are the easiest ones to look at. Everything else is a ratio, correct? I'm looking at x's over y's, y's over x's, 1's over y's, 1's over x's, and so forth. if you're taking a look at tangent and you're dividing y's and x's, just like cotangent, so we can actually do the tangent and the cotangent at the same time. We can divide by the number 1 and we can get back to the number 1. That's okay. But what happens if we divide by something between 1 and negative 1? What happens when you divide by a 1/2? You get a bigger number, don't you? When you divide by a value between 1 and negative 1, the number gets bigger. Agreed? Except for 0. If you're already at 0, of course it stays the same. 0 divided by any number is 0. So when we're looking at this range right here, on tangent and on cotangent, we actually get all real numbers. Because I can get a number of 500, I just have to have an angle measure that gives me an x value potentially of 1 over 500, right? Something like that. If I divide by 1 over 500, I get 500 back. Okay? So my range values actually end up being all real numbers. And then this is an interesting one for secant and cosecant because these are reciprocals of sine and cosine, correct? So actually what I get is I get a negative infinity to negative 1 union 1 to infinity. I'll explain the notation if it's something you haven't seen in a while. And you get the same thing for cosecant as you do secant. They match. Secant and cosecant are specifically reciprocals. Okay? So yeah, I can get really big numbers. But I can't do a reciprocal of 0, so I can't get 0. I don't have anything that would give me any values that would occur between negative 1 and 1 because I don't have numbers like 2. There is no sine value that's equal to 2, so I can't do a reciprocal and get a 1/2. Right? So I actually end up getting values that are sort of the complement of what the range values were on the other one, right? It's everything that the range values weren't, with the exception of the 1 and the negative 1. They do overlap at those spots. Okay, and we're going to take a look at actually using some of this information now. This directions, they use the fact that the trigonometric functions are periodic, which means that's that unit circle issue that we can keep going round and round the unit circle till the day is long and we still get the same values every time. Okay, that's the periodic business. To find the exact value of the expression, do not use the calculator. So when something says do not use a calculator, it often means you're going to get answers with radicals in it, which means you can use your calculator to check, right? But your calculator is not going to put it back into radical form for you. All right? So you're going to expect this often anyways on problems like these, you get radical solutions. So not radical as in, crazy and extreme, but radical as in the radical. All right, so we have 405 degrees, which is more than 360, agreed? So this is kind of going back to your question, Tyra, at the beginning of what do I do to show work, right? So when I'm taking a look at 405 degrees, the first thing I should see is that's more than 360, which means the periodic business is that I can subtract the 360. So if I take 405, or 405, and I subtract 360, what do I get? I get 45, and I really like 45 degrees. Why do I really like 45 degrees? Well, because that's a number between 0 and 90, right? And I like it because it's on my unit circle. So let me flip back over here for us. Unit circle, 45 degrees that you're going to memorize for me right there is in the middle of the first quadrant. I'm supposed to be doing tangent, which means I'm doing what? Sine over cosine or y over x. Yes? What's the y value here? Square root 2 over 2. What's the x value? So what happens when I divide them?
1.
I get the number 1. So this is one that if you check in your calculator, it's going to be able to handle just fine because I didn't get any radicals in the answer, correct? This is the number 1. Let me write it in since we just did that. This is square root 2 over 2 divided by square root 2 over 2. That way if you look back at this, you'll know how we got 1. And this gives me a solution of 1. I shouldn't say if you look back. I should say when you look back at this, right? Absolutely what I should say. All right, 17 pi over 4. So you should sort of feel like I did this on purpose because I want you to become more familiar with radians, and I'm not going to let you change it right now into degrees, okay? You can change them on your homework. That's fine. If you really hate the radians and you still want to kind of think about it now, it's okay. But we're going to keep working with radians more and more in class. So I have 17 pi over 4, and 17 fourths is more than 2. This is bigger than 2 pi. So just like the 405 was bigger than 360, this is bigger than 2 pi, which means I can subtract 2 pi from it. So taking a look here, I've got 17 pi over 4, and I want to subtract 2 pi. Well, 2 pi in terms of force would be 8 pi over 4. Everybody with me on that? Okay? So what is 17 pi over 4 minus 8 pi over 4? 9 pi over 4, but I need to do it again, right? So I'm not going to write that this is equal to 9 pi over 4. I'm not going to write minus 9 pi over 4 again over here. I'm going to do another one, right? This is 9 pi over 4 now, and I want to subtract that 8 pi over 4. Why am I subtracting 8 pi over 4 again? Because they have a common denominator. What is 8 pi over 4 equal to? 2 pi. Okay, so that's where that 8 pi over 4 is coming from. So what happens if I subtract this again? Pi over 4. Do you like pi over 4?
Yes.
It's okay anyway, right? Even if you don't like radicals and pies and radians and all that stuff, it's okay. Pi over 4 is in the unit circle. What degree measure does it correspond to?
45 degrees.
45 degrees. So it's a lot like the one we just did, yeah? Okay, but cotangent, very technically, is not y over x. It's x over y. In this particular situation, it's not going to matter. Agreed? But it is x over y, actually. So if we do this and we write this, we've got square root 2 over 2 over square root 2 over 2, and we end up getting what? 1. But do you think that just maybe that I'll know if you use your calculator for the whole thing? Because you're probably, well, you won't get a decimal. You'll still get the number 1. But probably if you use your calculator for the whole thing, you're going to forget that you should have shown any work that said otherwise. Okay? Yes?
Question. When we show our work, could we just divide 17 by 4 and know that the remainder is pi over 4?
Yes. Write down that that's what you're doing, though, for me. Somehow to indicate that that's what's going on. Yes, that's perfectly fine. And if you don't know what she said, that's okay. She's just thinking of it a little differently, which is awesome.
That's how I did it.
Yes, and you can do that too. Yeah. All right. Some even odd properties. These are some cool properties. So sine and cosecant have the same property because they're reciprocals, okay? So whatever I write down for sine, I'm going to write down here for cosecant as well. But I want you to take a look here and notice. So we're going to take over here, back to my unit circle for a moment. If I go up 30 degrees and I go down 30 degrees, okay, so can everybody picture what I'm doing? I'm going up the 30 and I'm going down the 30. My y values are almost the same. What's different about them? They're negative. One of them is negative, the other one's positive, right? So if I have a positive angle theta or a negative angle theta, I get the same y value except that one of them is negative. And that's what this is talking about right here. This sine value is the same as if I had done a negative and then I had done the sine of that positive angle. Okay? I get the same value, it's just that I get a negative instead. And cosecant, of course, because it's a reciprocal, you know, it has the same property sort of for free. Now let's look at cosine. So let's still go up my 30 degrees and down my 30 degrees. What happens to the cosine value if I go up 30 degrees or down 30 degrees? It stays the same, right? I have the same x value no matter whether I went positive angle or negative angle. So over here on these properties, the cosine value of a negative angle is the same thing as the cosine of a positive angle, which means secant has that property as well. Tangent, because it is division, right? So take a look at what's happening here. If I have tangent of negative theta, that means I have the sine of negative theta divided by the cosine of negative theta, correct? So what's going to happen? It's going to be negative, because I would also then be dividing negative sine by negative cosine. If I divide negative sine by negative cosine, I'm sorry, by cosine, get positive because that's not negative. That's an equal sign. So if I divide negative sine by cosine, I get negative tangent. So this is the negative tangent of theta. And I can do the same thing with cotangent. I would be dividing cosine by negative sine. Or I can think about the fact that what I just told you before is that if cosine and secant are reciprocals, we've got this property for both. I get negative, okay, I'm out of space. We're going to do it down here. I get negative cotangent of theta. You might be looking at this, I hope anyway, you're thinking, why did they call them even odd? This is a term again from algebra. Even functions, which these two are, have the property that if you have a positive input or a negative input, you get the same y value. Okay? An even function that you have seen before is a y equals x squared, right? A parabola. You have a parabola. One of the ways we talked about something being even back in algebra is that if you folded it in half, it was the same picture on both sides, right? So if you do your hands and you go like this, right? This is an even picture because you've got the same mirror image on both sides, okay? The other four on here are called odd functions. So these two and these two are odd functions. And they have the property that if you have the negative on the inside of the angle, in this case it's an angle, but the negative on the inside with x, it's equivalent to having a negative on the outside of x. Now, a function that you've seen that was odd before was y equals x cubed. Okay, so y equals x cubed will look like this. And visually, it had the property, from a visual perspective, of being able to sort of rotate it around 180 degrees, and it lands back on top of itself. And when we get to graphs, you're going to see these properties at play in the graphs of these functions as well. So cosine and secant are going to have this sort of a mirror image property. And sine, tangent, and their reciprocals are going to have this sort of a rotation property in them. Okay? But knowing them now allows us to be able to compute values that have these properties. And if you take a look at this one on 3 and 4, we can use this fact. So if you take number 3, this is sine, which means what happens to the negative? Does it go away or does it come outside?
Comes outside.
It comes outside. So the first thing, because this says use the evenodd properties, we want to show that it's actually doing that. This is negative sine of 135. Okay? Which means the negative is going to be part of the solution, and then I can use my unit circle, because it's all in positive angles on my unit circle written, right? I can use my unit circle, and I can actually go to the 135 degrees. Where is 135 degrees located? Which quadrant? Quadrant 2, and it's the one that's actually giving me what sine value? Square root 2 over 2. It's a 45-degree angle, yeah? This is square root 2 over 2. And the sine value there was positive, right? We're right here. Sine is y is the square root 2 over 2. So the sine value itself is square root 2 over 2. The negative is coming from the negative that was originally inside with the 135, and we moved to the outside. Okay? All right, secant of negative pi. Well, what happens with secant to negatives? They go away. I don't even need to use them, do I? I don't. And so I can rewrite this simply as secant of pi. So where's pi? It's at the 180, so it's over here on the negative x-axis, right? And this should be the cosine values reciprocal. So this should be the same as 1 over cosine, or 1 over, I'll do it this way, 1 over x. And what is x at that point? It's negative 1. So 1 over negative 1, and my solution then is negative 1. So my secant value there is negative 1. All right, so here is sort of combining some of the facts that we've been using. Again, exact value of the expression, do not use a calculator, da-da-da-da, we got all these rules, right? So the first thing is that I have tangent of a negative angle. So what am I going to do with tangent of a negative 6 pi? What do I do with a negative, TJ?
Keep the negative.
Keep the negative and pull it out, right? Yeah. So I'm going to pull this negative out here. So this is going to say negative tangent of 6 pi. And we'll deal with that 6 pi in a moment. Let's just deal with the negatives first. You can deal with more than one at a time when you're working. But for me right now, we're just going to go with one at a time. All right, 6 pi. Where where am I if I'm at 6 pi? I'm at pi? Actually, it's 0, aren't I? How many full times around the circle would I've gone if how many full times around the circle would I've gone if I've gone 6 pi? 3 times around the circle, right? And this is one of those things like what you were saying. I'm going to forget your name. Ashlyn, right? This is what Ashlyn was asking about a little bit before. 6 pi is actually an even pi, correct? All of your even pi's are going to end up over here on the positive x-axis, and all of your odd pi's are going to end up on the negative x-axis. Agreed? So this is the same thing as having negative tangent of 0, or 0 pi or whatever, okay? How about 9 pi over 4? We've actually seen 9 pi over 4 today. So what do we do with 9 pi over 4? We subtract, what do we subtract? 8 pi over 4, because that's equivalent to 2 pi, which means we get a grand total of pi over 4. You guys are going to be good at pi over 4s today before you're done. So this is cosine of pi over 4. All right, so tangent should be y over x. So I'm going to write this in as y over x, and then we'll actually fill that in a moment. Well, actually, let's do it now. What is the y value at 0? It's 0, isn't it? I've got the ordered pairs 1, 0. The y value is 0. Just for kicks, what's the x value? 1. And then 0 divided by 1 is? 0. So I've got 0 coming out from this first part. Okay, I'm not done. I'm only doing half of this picture at the same time. Cosine pi over 4. So at pi over 4, where am I? What quadrant? Quadrant 1. Cosine is which value, x or y? So this is the x value that I'm looking for. It is square root 2 over 2. So what is the total for this equation, or this expression? Square root 2 over 2. You do not have to show the x's or y's, but I'm wanting to remind you where those are coming from, since this is sort of a new topic for us. Any questions? Okay.